Okay, let me just do a little bit of recap from what we've done with volume so far. So far, all the shapes that we've been finding for volume have been resulting in rotation around the axis. So everything has been circle related because of that rotation. But now we're going to talk about, what if we were building cross sections or the shapes that results if we cut the object in half, other than circles. What if, because for this method and wash method, if we were to slice it down the middle and open it up, we're going to see circles. Right? But as we look at, well, what if we can create these volumes of shapes that are where the cross sections are not circles? What if the cross section are squares or rectangles or semicircles or equilateral triangles? They're going to end up looking like very odd shapes, and we don't have to really worry about how to graph these shapes, but we just have to do some slight adjustments to get it into a formula to find the volume of these objects. So I just want to kind of give you a quick, I'm not able to really draw these graphs very well, but if we were, these really don't have any names for these objects. So if we had objects that had triangular cross sections, it could look something like this, or an object with a square. This is the base, and you're building on top of the base a square cross section. This would be cross sections that is made up of triangles. Cross sections made up of squares again. And this is cross sections made up of squares. You got a cross section here made up of semicircles. All right. But the good thing is that we just have to make a slight adjustment with the formula that we've learned, and that will get us into finding these volumes of these objects. All right. All right, so the volume problems we've covered so far, Disk and Watcher, have involved taking the shaded region and rotating it about the center, resulting in a circular area. And area has so far been pi r squared, or pi big R squared minus pi little r squared. And so all we're going to be doing is we're just going to be adjusting the area that we want to build, whether it's going to be, right now they've been circles, but eventually they could be triangles, rectangles, squares. And then once we find the area of that shape that we want to build, we just put an integral in dx around it, and that will accumulate from one end of the boundary to the other. So we're going to do a problem that is based off of this. Now, we're going to be starting off with a base. The shape of the base is not important. Right now, it looks like a kind of a quarter circle here, but that's not important. The important thing is we understand this is the base, and then we're going to be building these different shapes on top of it. In this first example, we're going to be building squares on top of the base. So you can imagine these squares, if they're vertical squares, vertical length, all the squares will get larger and larger as our length gets longer and longer. So the square here is going to be really small, but then the square here is going to be a lot larger. We can see that in this case here. All right, so example one. For those of you coming in late, we're on page 17. Okay, so our goal for our first example, we're going to try to find the volume of this object. Okay. All right, so example one, find the volume of the solid that's bounded about the curve y equals root 1 minus x squared. So something like this. Y equals 0 and X equals 0. So we have our shaded region here in the first quadrant. And the cross sections are squares. So we're told what shape we're building on top of the space. So imagine this space as standing or existing on a flat surface. And then we're going to be building these squares that's going to come out of the page. Okay. And you're also told how to draw your length, okay, parallel to the y-axis. So parallel to the y-axis is vertical. Parallel will stay vertical. So we want to create these vertical base lengths. So for area, if we're trying to find an area, we would call this the height of a rectangle. If we were dealing with rotation around an axis, we would call this the radius of either for either disk or washer method. But now we're calling this the base length of these squares that we're going to be building on top of the space. Now, the good thing is that anytime we see a vertical length, you're going to do the same thing as area or disk or washer method. You're just going to do top minus bottom. Okay, so we'll do top minus bottom. But we're going to call it the base length. So the top of the base length is sitting on the curve, and the curve is named root 1 minus x squared. Minus 0, because the bottom of the base length is sitting on the y equals 0. So our base is simply root 1 minus x squared. Okay, we are building squares, right? We're building squares. So we look at the area formula for the shape that we're building. So the area formula for this particular shape that we're building on top of this base. Again, I know this looks like a quarter circle here, but the shape of the base doesn't matter. We're building, you know, the base can be any shape. It doesn't really matter. But we're always told what shape we want to build on top of this surface. Okay? So the area for a square is base squared. So we're taking our base, putting it into the area that we are working on. And now that we have the area of one of the squares, the next thing we need to do is just to put the integral notation around it, and that will accumulate all these different sized squares from one boundary to the next, from one left boundary to the right boundary. So because we're doing top minus bottom, our bounds will stay in terms of x. So now our volume is just the integral from, and then all we're doing is we're kind of building everything up in stages in terms of dimensional stages. So we start off with one-dimensional information, then we got it to a two-dimensional information, and then the integral will give it that third dimension for us. So root 1 minus x squared dx. Now, because we're doing top minus bottom, our everything is in terms of x, which means our bounds are also in terms of x. So we look at the furthest left x value of our shaded region is 0. The furthest right value, you can set this equal to 0 to find that x-intercept. You could also graph it in your calculator to find that x-intercept, which is simply 1. And now the rest is just calculator. I feel like some students are tempted to put pi in front because that's what we've been doing with disk and washer method, but there's no rotation. If there's no rotation, there's no circular shape, so there's no pi with most cross-section problems. There is one exception. We are building sometimes we are asked to build a semicircle. So semicircle does have a pi involved, but most of them are not circle related, so there's no pi in front. And the rest can just go in your calculator. Math 9, integral from 0 to 1, square root of 1 minus x squared quantity squared. And that'll get you 2/3. And it's still volume, so cubic units. But for cross sections, there's no dotted line, there's no rotation. We're just building these shapes on top of the base. Okay. And really, we're not really going to be drawing any of these three-dimensional shapes. All we're going to be doing is we're going to build the base, find the bounds, put it into our area formula, and then put integral around it. Okay, any questions? You know how with disk and washer method, the problem always gets you whether you're rotating around the x-axis or y-axis or vertical axis or a horizontal axis, and then from there you build your radius. For these problems, you're always going to be told exactly how to build your base length. So, but instead of telling you it's vertical or horizontal, they'll say things like, well, the problems will say things like parallel or perpendicular to the y or the x-axis. And from there, you have to interpret which direction is that base length. So in this case, parallel to the y-axis, that's a vertical base length because parallel to the y-axis is still vertical. Okay. But I just want to show you that there are 4 ways of representing vertical or horizontal. And if you just pay attention to parallel, or if you pay to just x or y axis, you may not fully think about what direction it is. So I want to show you the 4 ways that we can say horizontal or vertical. And I'm going to put this at the top of the page so that I think this is a potential issue on test or quizzes. Sometimes we assume, oh, I see parallel, so that must mean vertical, or I see y-axis, okay, so that must mean vertical as well. So let me write down those 4 variations of directions. Put this at the very top. So one variation is parallel to the y-axis. We can also say parallel to the x-axis. We could also say perpendicular to the y-axis. We can also say perpendicular to the x-axis. So we just pay attention to both words and just visualize, which direction this is talking about. So let's see if we can go through each of these and make sure we understand that we need that there are 4 different variations, but they're either talking about horizontal or vertical. Okay, so parallel to the y-axis, which direction is that? Vertical. So I'm going to say vertical base. Okay, parallel to the x-axis. Horizontal, right? So that's a horizontal base. Okay, perpendicular to the y-axis. That's horizontal, right? Y-axis is vertical. Perpendicular means I got to make it 90 degrees away from that initial vertical. So this is going to be horizontal. Perpendicular to the x-axis. Vertical. Okay. So when you see these problems on the quiz, just slow down and just pay attention to those words and just visualize, that direction. All right. So put those two words together, get a visual on that direction, and then go from there. Because I hate for students to just look at, let's just pay attention to one word, and they assume that it's a certain direction, and then that throws off their entire problem. So just slow down when you see one of these four options, and there's no need to memorize this, right? You can just visualize, okay, this is my x-axis perpendicular. Okay, so that must be vertical. Right? So I don't want you guys to feel like you have to memorize this. You should be able to figure that out just by slowing down and looking at those two words combined together. Okay, let's go to the back page. Okay, find the volume of the solid of the base bounded by the curve y equals x squared and line y equals 4. So first things first, we're just going to figure out what the shader region is looking like. So we have y equals x squared. That's a parabola that goes through 0, 0. And the line y equals 4. Okay, so there's our enclosed shaded region. The shape of the shaded region doesn't matter because they're going to be telling us what we're going to be building on top of the space. So we're building isosceles right triangles whose hypotenuse lie on the base. And then we're talking about base length that is parallel to the x-axis. So which direction do we want that to be in? Parallel to the x-axis. Horizontal, okay. So horizontal base from one end to the other. And just like previous problems, anytime you see a horizontal base length, horizontal height, or horizontal radius, there's additional work ahead of you. Okay? You know that the equations that's given to you is not going to be in the proper form that we need. So we have to get our equations into a different variable in terms of x. All right. We're going to be stacking these isosceles right triangles, which we don't see because these triangles are going to be kind of jutting out of the page. But again, we don't have to draw this out. We just have to be able to identify the base length, put it into the formula, and then put integrals around it. Okay, so y equals x squared, that is not going to be in the proper equation that we need. We need to solve for x. To solve for x, I got to take the square root of both sides. So x squared is equal to y. I just want to get that x on the left side. Take the square root of both sides to solve for x. I get plus or minus square root of y. And plus or minus square root of y. This actually ends up giving us two equations, which we need both equations because they will act as different sides of the parabola. So we have x equals root y for the positive first quadrant portion, and then the x equals negative root y is for the negative version. So this portion is the x equals root y, and this portion is the x equals negative root y. Now that we have both equations in the proper form, if we see x equals on the left side, the right side is going to be fit or ready for a right minus left relationship. So our base length is right minus left. So the right endpoint of my base length is sitting on the root y minus left. The left endpoint of my base length is sitting on the negative root y. So what's root y minus negative root y going to get us? Two negatives cancel out. We get what? 1 root y plus 1 root y, which is 2 root y. Yep. Okay, we have one-dimensional information about this problem. Let's move on to the second dimensional, which is the area. In the area, we want isosceles right triangles whose hypotenuse lie on the base. So hypotenuse on the base is going to be this formula here, 1/4 base squared. So 1/4 base squared. And we're just updating the base with what we found for our problem. And then our final step, volume, integral, 1/4 2 root y squared dy. And because we are dealing in terms of y here, we're stacking these triangles from the lowest to the highest y value. Sometimes we have to set equations equal to each other. I think in this case, we can kind of just tell what the lowest and highest y values are. The smallest or lowest y value is what? 0, and the highest y value is 4. Yeah. So sometimes it's easy to tell. Other times you may have to set equations equal to each other when, if they're like two curves that are intersecting at a point. But in this case, it's just a nice horizontal line that's showing us our boundary. Okay, the rest you can plug in the calculator. I figured maybe it's easier to do some cleanup here so that your calculator doesn't have to go through as much multiplication, but I can just square this 2 and root y here, and I just made it integral of y dy. But you're welcome to plug in at this stage, or you can just continue working out by hand. 16/2 is 8. Don't attach pi. There's no rotation going on, and it's just 8 units cubed. Okay, example 3. Find the volume of the solid if the base bounded by the curve and the cross sections are semicircles. So now we're building semicircles whose base are perpendicular to the y-axis. All right, so actually, if you look, it's the same equation, same curve here. So we'll graph the curve. Okay, but this time, look at the wording here, perpendicular to the y-axis. Which direction is that? Still horizontal. So same orientation, but different ways of saying it, right? So that's why I think it's good just to slow down, look at your two words, look at how they're combining, visualize it, right? Don't assume, okay, if I see y-axis is this direction, or if I see parallel is this direction, make sure that you're paying attention to both words and combining those two things together. So this is still horizontal, right? Still horizontal. So I guess that's nice because for this problem, we can reuse a lot of information. Same base, same bounds, we're just building a different area. So in this case, our area is pi/8 base squared. Go ahead and update your base. And then once you have your area built, then you're just putting an integral around it. I'm going to, so this is the only time you got to keep track of a pi when there's a semicircle. Not because of rotation, but because we're actually building something that's circle related on top of our base. So I like to hold on to the pi. So you can plug this in the calculator and then multiply by hand pi over 8 through. I just worked this out by hand. 4y became 4y squared over 2. Plugging upper and lower bound, I got 32. 32 divided by 8 is 4, and I'm attaching the pi there. So 4 pi is my units cubed. But if you plug this in the calculator, you can also do that as well, and you'll get the same thing. You'll get 32, and then multiply the pi over 8 by hand. Okay, example 4. Let region R be the area enclosed by the function y equals natural log of x. That's the curve you see here. And 1/2 x minus 1. That's the linear graph here. If R is the region of the base of a solid, that is each cross section perpendicular to the x-axis. So here you're told which direction to draw your base length. We have an isosceles right triangle with a leg on the base. So let's figure out which direction is this going to be. Perpendicular to the x-axis. Vertical, right? X-axis is this way. Perpendicular, it's going to force it 90 degrees, going vertical. So you know that you're back to a top minus bottom, which should make it easier because there's no need to adjust these equations. These equations will be good to go if you see a vertical base length. Just like if it was a vertical radius, just like if it's a vertical height, we tend to have a little bit easier time there. So let's build our base length. Top minus bottom. The top of my base length is sitting on the natural log of x. Minus, and the bottom of my base length is sitting on the linear graph. Careful though, anything that comes after a minus sign, we do need to protect that with a set of parentheses. We do need bounds. The bounds are going to be hard to do by hand, so you may have to plug this in the calculator and do your second trace intersect feature to find both of your intersections, which will be used as your bounds. But let's go ahead and build the area as well. Area, isosceles right triangle with a leg on the base. So if you go to the top of the page here, isosceles right triangle with a leg on the base is 1/2 base squared. I'm just going to distribute the negative through, so I don't do deal with as many parentheses. So I'll make this one natural log of x minus 1/2 x plus 1. Now I'll go with my updated base length within my area. And then my volume. Integral of 1/2. Okay, all right, let's find those intersections using our calculator. Okay, so y equals natural log of x. Y equals 1/2 x minus 1. You can say 0.5 x minus 1, so you don't have to deal with fractions. Oops, stop. I hit graph, or I do zoom 6. If you don't like how that graph is looking in terms of, it still looks a little bit zoomed too far, zoomed out, where you can't, it's hard to distinguish that space in between. So if you do second trace, sorry, zoom, click on zoom, and if you do zoom box, you can draw a box around that region that you want to zoom in on. So I'm just moving my cursor to where I would be a good spot for the upper corner of my box. Hit enter, and then go ahead and draw your box using your directional arrows. And once you have the box drawn, then you can hit enter again, and then it'll zoom in on that box. That's much better. Second trace, intersect. So I'm going to scroll to a point to the near my left intersection, hit enter, enter, enter a third time. I get 0.464, 0.464. That's my left bound. And then now we're going to do second trace intersect again. This time I'm going to pick point close to, make sure that you never put your cursor directly on the intersection, because then it'll confuse the calculator. So just pick points close to it and let the calculator find it for you. So as long as you're close to the intersection, the calculator will know, okay, you want me to find this intersection on the right and not the one on the left, because we're closer to that intersection. Okay. 5.357. And now you can enter this in your calculator, Math 9, or if you want your Y1 to hold your base length, you can. But practice plugging that in. Let's see if we get this volume. Any questions? I do want to point out that we are responsible for these formulas here. I know that seems like a lot, but let me just kind of go through them so that you can kind of see the patterns here. Well, we know square is just length times width, so that should be easy, right? Base times base, so that's it should be easy to do. We know rectangle is base times height. We'll talk about some problems with rectangles a little bit later, but if it's a cross-section problem, they have to give you very specific information about what the height is. So they'll have to provide the directional information about the base, and they have to give you very specific information about the height. So just know that rectangle is base times height. Now, all these look a little bit more intimidating because you have all these formulas that look very different. But what do you notice about all these formulas here? What similarities with this? That they all have what? They have base squared. So understand, okay, all the formulas have base squared except for rectangle. Rectangle is base times height. So the only thing you have to worry about is the coefficients that's going to go in front of the shapes. So isosceles right triangle with leg on the base is 1/2 in front. Right triangle with hypotenuse on the base is 1/4. Equilateral triangle is √3/4. And semicircle is pi/8. So you have 2, 4, 4, 8, and then you just have to make a slight adjustment with the equilateral triangle with √3 up top and a semicircle with pi up front. But if you know that, they all have base squared, and my coefficient in front is just some fractional value, hopefully that makes it where it doesn't feel like, oh, we're just finding these formulas that are just kind of slight adjustments from each other. Okay, I would like for us to go to, because we are going to have a quiz on Wednesday. So I want to kind of go through each of the derivative and integral formulas just to kind of talk through them as you guys are preparing for. So is anybody missing this handout? Okay, I'm just going to go through the key version here. Just want to talk through each of the rules as you guys begin preparing for your quiz. I still have. Right now, okay. Okay, so first, derivative rule. This is derivative rule that has, so basically all these have chain rule built into it. So I want the rules to all include that u prime. So we know derivative rule, this is the very first rule that we learned first semester. We bring down the exponent, subtract 1 from the exponent, and multiply by the inside portion's derivative. Derivative chain rule, f prime of g of x times g prime. Trig derivatives, we've been, so everything will be laid out like this. So you know that all the C functions will produce negative derivatives, and the ones across from each other, they all have a similar form. Secant and cosecant kind of have similar form. Secant, tangent, and secant involves each other in terms of their derivatives. Cotangent and cosecant involves each other in terms of their derivatives. By the way, I just want to make sure that we're following along on the key, which is attached to your blank version, and hoping that you guys can save that blank version for you to practice. But I can also provide you some additional blank versions tomorrow if you want some more practice worksheets. Okay, natural log and e to the u, these are big ones here. Natural log is u prime over u. E to the u is e to the u times u prime, basically itself. Log base a of u is just a variation of natural log of u. They both have u prime over u. We just need a bit of conversion in front, so 1 over natural log of a. E to the u and a to the u, they're both exponential functions. They're both original functions times the exponent's derivative. But a to the u has a little bit extra with conversion, so times natural log of a. Arc trig, we know that the left column are the only unique ones. The ones on the right are just the negative versions of the ones that you see immediately to the left. So if you know these three, you can just copy the ones to the right and just put a negative in front. All the arc trig has derivatives have u prime above, and all the denominators have 1 and u squared. It's just different ways of combining. I like to start here. My arctangent is easiest looking, 1 plus u squared. And then I like to move to the arc secant. And I know that there's an absolute value in front. I know that u squared minus 1. And I know this u squared minus 1 because I know the u's are next to each other. So that helps me remember, okay, the u's are next to each other. I'm going to put that first. And if I see u squared minus 1, then I can go up and change my arc sign or create my arc sign with a slightly different variation. So if I can see that in front of me, that helps me remember to create my arc sign. Okay, integral rules for trig. We know these are just opposites or going backwards from our trig derivatives. Right? If cosine becomes negative sine, then sine will become negative cosine, and we're just reading off of the trig derivatives, right? Okay. We have 4 trig integrals that involve natural log. So what helps me remember is that I know tangent is sine over cosine, and I know that the denominator is what's going to show up. And I see a C letter showing up as the first letter within, and so that C helps me remember, okay, there's also negative as well. Cotangents, antiderivative. I know cotangent can be written as cosine over sine. And if I can spot that sign in the denominator through u substitution, I know that's what's going to show up in my natural log. I see a S. This is not a C, so that helps me remember I'm dealing with a positive here. Secant looks a lot like the secant derivative, except it's with a plus sign in between and with a natural log. I don't see any C starting off my absolute value terms, so that's positive. And then cosecant antiderivative looks a lot like secant. It's just a different, same form, but different functions. I see the letter C, so that helps me remember inside the absolute value, so it helps me remember to keep that negative. Okay, back page of the power rule for antiderivatives. Add 1 to the exponent divided by the new exponent. 1 over u du, that's natural log absolute value of u. E to the u is just e to the u. And a to the u is just a to the u, but we need a conversion, so it's 1 over natural log of a in front. These are the most recent rules that showed up on the most recent test. So you know that anything with the multiple u's, this kind of looks like the arc secant. We do need to include that absolute value. There's no radical in the denominator. That should help remind us we're dealing with arc tangent. And then the square root of a squared minus u squared. There is no 1 over a. It's just arc sine of u over a plus c. Okay, different variations of first fundamental theorem. First is if I have integral from a to b of lowercase f, it'll become uppercase f of b minus uppercase f of a. And that lowercase uppercase is just whatever it takes to get from my function to my antiderivative. There's one variation. In these variations are just sometimes at the derivative level or at dealing with a particle motion. So if I start with velocity, then velocity will rise up to position, so x of b minus x of a. If I'm starting with f double prime, it'll rise up to f prime, so f prime of b minus f prime of a. If I start with acceleration, my acceleration will rise up to velocity, so v of b minus v of a. 2 variations of second theorem. Second theorem, you know that if you see derivative and integral next to each other, they're going to largely cancel out. So the f is not going to change, but the upper bound is going to have a slight impact. So it's f of p of x times p prime. But and we can ignore the a because a is a constant. It'll just end up washing out. But if both the upper and lower bound are variables, then we got to do the process twice. Once for the upper bound and once for the lower bound, and we put a minus in between. Okay. Average value theorem, 1 over b minus a, integral of a to b of f of x dx. Area of a trapezoid, 1/2 width times height 1 plus height 2. And then the general solution for a y prime equals ky, y equals ce to the k2. Now there's like 40 or so formulas here, but the quiz will only have 20. Okay, but what I'm going to do is I'm gonna have the quiz stapled to the blank practice sheet so that you have the blank practice sheet in front of you. And then, if you're practicing with the blank practice sheet, then you can use that as a way of remembering where different parts are, and everything will be laid out like this. But I'm only going to be grading the quiz, which you can just, if you want, you can use the blank practice sheet to fill out first, and then fill out the quiz, or you can just use that as a reference sheet. But the quiz will only have 20 random. I'm just going to pick 20 random ones from the blank practice sheet onto the quiz. And this will be a quiz grade on Wednesday. Any questions? So tomorrow, I'll give you some additional blank worksheets if you would like it. And then Wednesday, I'll give you guys 5 or so minutes to look over and do some practice before you take the quiz. But after the quiz, we're going to start our quiz review for our area volume. Okay, your homework tonight is page 5 and 6. I didn't get a chance to check page 3 and 4. So tomorrow I'm going to check pages 3, 4, 5, and 6. All right, come get your phones.
Shut up.
Okay, yeah, go ahead. Sure.